Okay. All right, so this is what we ended up last time. Algorithm analysis. And the whole idea of algorithm analysis was, well, first, what do we mean when we say one algorithm is better than another? And we talked about some really important things. One of it was like lines of code, which that's a good metric in a way, but not a good metric in other ways. There was code understandability, which is a big one. But of course, there was the really big important one that we were actually talking about, and it's how much resources your algorithm actually needs. And it's important to have an understanding about that because sometimes you might have a design decision to make. Sometimes you can have two very different algorithms for solving the same problem. They're both right. But in some situations, one algorithm might excel where the other one doesn't, and vice versa. If you've got an algorithm for solving some problem, but the input data is coming in a certain way, maybe one type of algorithm is better than another. But the point is, by having an understanding of algorithm analysis and what it means for one algorithm to be better than another one, it equips us with the tools to make informed decisions about what is a better implementation. Now, everything I'm going to talk about right here, for the most part, is going to be based on the mathematics of computing, of computation. So everything I'm talking about, obviously it's connected to the code we write. But I'm talking about it at the mathematical level, about what things are true mathematically, what things are true as a property of this universe as existing through our mathematical definitions of these ideas. And I'm not being all hand-wavy with that. That's what I'm doing. Some of these ideas might not carry over to practice in certain situations, and I'll talk about some of them. But anyways, the big one we're going to hit is time complexity. Space complexity is another really big one as well, but we're going to talk a little bit more, we're going to have a bit more of a focus on time complexity. How much computing resources does our algorithm need? And really, we don't care about how much computing resources. When we're talking about complexity analysis, we don't care about the amount of computing resources in an absolute sense. We want to know how much work this algorithm takes on some arbitrary sized input, and how the amount of work changes as that input size changes. So it's more abstract, let's say. So how long does an algorithm take based on some input size? How long is it going to take on 10, an input size of 10? Like how long does it take to sort a list of 10 things versus a list of 10,000 things? That's kind of the idea here. Obviously, there is an important question to be answered when I say how long is it going to take with 10 things. If your data is always going to be size 10, that's a very meaningful piece of information to you. But when we're analyzing the algorithms more generally, these are the questions we're asking. So we want to consider the number of operations needed for that algorithm to do its thing. Operations being things like additions or comparisons. They all might take a little bit extra time or a little bit more time than one another in terms of number of clock cycles, for example, on your computer. But the point of this is adding two numbers doesn't really change. It's constant time. If I'm adding the numbers 7 and 8, and I'm adding the numbers 20 and 28, there's nothing to scale with input size. I'm just adding numbers, right? It's not like with the idea of a list of a linear search. I'm searching over some collection. Adding two numbers, those are constant time operations. The amount of time it takes really doesn't depend on input size. In practice, technically it could, based on how the systems that we use work, but for our purposes, we're considering them all to take constant time. It's not that they all take the exact same amount of time, it's that the amount of time they take isn't going to change on the input size. So for all I care, they're all constant time operations. And yeah, so a growth function. I was talking about how long does this algorithm take relative to the input size. So what we want to do is define a growth function. Before everything I'm going to say, let's not worry about how we're deriving a growth function yet. That's not important at this stage of the discussion. Let's say I've given you this growth function, and just hang in there with me. You've got this growth function. So we define a growth function called t of n. The amount of time this algorithm takes as a function of n. If n is 10, how long does it take? If n is 100, how long does it take? If n is a billion, how long does it take? It's some function. How long does it take? Yeah, okay. So t of n is the growth function. Okay? We have no hard numbers yet, but it's a growth function. And notice how t of n is a function of n. Yeah, I just said that. And it means that the amount of time it takes depends on what n is. In the context of this, n is like the input size. Like, how big is that list, for example. So let's say I have a growth function that looks like this. T of n equals 15n squared plus 45n. Okay? That is my t of n. Where it came from, don't worry about it. But if I go and I start to tabulate how much units of work this is going to take, I'm going to do it something like this. Well, if n is 1, the 15n squared part, because we have 15n squared plus 45n. And then they're just added together. Okay? So the two parts are important, but then we're just summing the two separate parts. That's all. So the 15n squared, when n is 1, takes 15 units of work. 45n takes 45 units of work, and the sum of them together, the total amount of work, is 60 units of work. Right? That's when n is 1. If I ask you, when n is 1, which of the two parts takes up the majority of the work? It's not a trick question. Which, if you're playing the blame game, who is responsible for making that 60 as big as it is? The 45n part. Let's say when n is 2. Well, when n is 2, 15n squared is 60 and 45n is 90. And the sum of that is 150. If we play the blame game again, who gets the blame? 45n. Let's jump to n is 5. 15n squared is 375 and 45n is 225 and the total is 600. Who gets the blame now? 15n squared. And chances are, if you know anything about mathematical functions, you were just waiting for the n squared to start to take over. Things that are squared grow a hell of a lot faster than things that are just that are linear, right? N is linear, it's just a straight line. Squared, you get that parabolic thing, right? And as we go, because remember, I kept saying, like, I really don't care about any of these absolute numbers. When I calculate t of n when n is 1, when n is 10, 100, a million, I don't really care about that specific number. But what I'm doing here is I'm showing you two things. How the individual parts can change who's more responsible for one of it. But as n gets bigger and bigger and bigger and bigger and bigger, it becomes real damn clear who's to blame for the majority of the work. When n is a million, 15n squared is 15 million trillion, I think that's a trillion. And 45n is 45 million. Now don't get me wrong, 45 million is a lot, but 45 million is tiny compared to 15 trillion. In fact, as n gets bigger and bigger and bigger and bigger and bigger, the amount, the 45n, the amount that we can blame 45n for the total amount of work gets smaller and smaller and smaller and smaller and smaller. Look at when it's 100. Someone do the math for me. What is 45,000 divided by 154,500? Here, let me do that. 4500 divided by That's what it was, right? So it's almost 3%. Right? But let's say I do, 45 million. That becomes whatever, times 10 to the negative 1, 2, 3, 4, 5, so 3. Times 10 to the negative 3 of a percent. As n gets bigger, the amount the 45n matters gets smaller and smaller and smaller. Or conversely, as n gets bigger, the amount the n squared part, the amount the quadratic part, the squared part, matters gets bigger and bigger and bigger. And when n gets even bigger, the 45n is going to account for less and 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 less. I kind of don't really care about 45n. In the grand scheme of things, it makes very little difference. So this table shows, okay, and let's plot. Here's a plot of, there's 3 lines on this plot. Trust me, there are. There is a line for 15n squared. There is a line for 45n, which at this scale looks pretty horizontal, doesn't it? And that's because at this scale, compared to 15n squared plus 45, which is the green line, compared to that green line, the linear part is it's so little that it looks horizontal. Now who can tell me where the third line is? Where's the blue line?
Under the green.
It's exactly under the green because the difference between 15n squared and 15n squared plus 45n matters so little that we can't even visually tell the difference at this scale. Here's the good news. Computer scientists are so lazy that when we do our math, we don't even want to be precise. Here what we would say, I'm jumping ahead a moment, here we would say like, you know what, 45n squared, or 15n squared plus 45n, let's keep it simple, let's just say it's 15n squared. And we get away with that because where the hell is 15n squared versus 15n squared plus 45n? There's objectively no important, meaningful difference here. And on top of that, we like to talk about how the t of n grows as a function of some other function. How it grows as a function of some, we've got like a set of common growth functions that we like to refer to. One of them is quadratic, n squared. 15n squared plus 45n grows like n squared. It asymptotically like n squared. It's not exactly n squared, but it's so close that we really don't care about the difference. Okay, figure compare, Notice how 15n squared is perfectly covered, yeah? Okay, here, warning. This is an important warning. I tried to emphasize a moment ago too, but I'll re-emphasize it. I'm just going to read it. Students tend to miss, when first learning this idea about computational complexity, is that the function describes how things change relative to n. The discussion's not about any absolute runtimes at this point. I don't care about the runtimes. I care how long is this algorithm going to take as a function of n as n just gets bigger and bigger and bigger and bigger and bigger and bigger and bigger. That's what I care about. That's what's meaningful. So given the growth function n squared plus 999n, one may think that 999 part of the function is going to dominate for all numbers n less than 999, which is true, but it's not the point of complexity analysis at all. The point is identifying which part of the growth function grows faster. And n squared grows faster. And I don't care about any specific absolute number like n 999. This is not in any way to suggest that that 999 part, that linear part, is not important or not valuable when you're making your decisions as a programmer. What I'm saying is that at this high level view of this function, it's non-dominating compared to the n squared. Any questions about that?
So I'm guessing one of the easiest ways to figure out which one dominates then is just to set it to either like basically infinity or just a really high number.
Well,
Like
you know what? It's going to get even easier than that. If at any point you're thinking, oh crap, math, don't worry, I'm thinking the same thing. We're going to try to hide all the math. Computer scientists like to do that. Computer scientists need to be tricked into doing math, if you haven't realized it yet. The reality is, computer scientists, all programmers are mathematicians, they just think they're not. Right? They just do their math a little bit differently. Sorry, I hate to break it to you if you didn't realize it. Who here likes math? Who here doesn't like math? Got bad news for you, you do, you just don't realize it. All right, so asymptotic notation. This thing we call it big O. This would be like, I've got some growth function, and this is where I go like, well, that growth function grows like this. Constants, things that take constant time, we don't care about them. Well, let me put it this way. When trying to derive a growth function and understanding how a function grows, constant time things don't have an impact on the growth function unless everything within that function is constant time. And then, well, we would say that is a constant time algorithm, which is nice. We like constant time algorithms. Non-dominant terms, so like in the previous example, that 45n, we don't care about those. The growth function itself really isn't that important, but it's the asymptotic complexity that is important. My growth function grows like this function. We love this function to fall within a set of common growth functions that one, are easy to understand, and two, really just tend to pop up a lot as a consequence of how we write our algorithms in computing. So, it looks like there's a syntax error in my stuff there with that asterisk next to the of. But, so asymptotic complexity, that's like the time the algorithm grows like the function, right? So the order of an algorithm is specified in what we call big O notation. The above example, t of n of 15n squared plus 45n, has an order of, so big O of n squared. Since it grows like n squared. So I don't care about these scalars here, this like constant out front of the n squared. I don't care about that. I also don't care about the 45. When I have something that's n squared and n, the n squared is what I care about. Now mind the difference here between the additions and the multiplications. It's the addition parts that, it's between the additions where I can make the distinctions. If I saw n times n, I wouldn't throw away one of the n's. Well, n times n is n squared. So just be mindful of it's like the additions, where you like add the things together and what part dominates and whatnot. So here's some example hypothetical growth functions and their corresponding big O notation of what they grow like. So if we have some t of n that's 17 units of work. Well, 17 is just, 17 is 17. If I asked you what t of 4 is, what's the answer? T of 4 for the function t of n equals 17. What's t of 4? 17. What's t of a million?
17.
It doesn't change based on n at all, does it? It's constant. So we say that's big O1. If we have a function, constant time, we like that. Now if I have t of n, that's 20n minus 4, well, we don't care about constants. when trying to find it. Like we play the blame game. Who does the most damage here? And there's an n, but there's really nothing else going on there. So this is a linear one. This is order n, big O n. It grows like a linear function. As n gets bigger, the amount of more work I have to do grows linearly. Here's one. 12 n log n. By the way, almost always. Raise your hand if you like logarithms. That's what I thought. If you love them. No one. Well, I got good news. In computer science, we use logs, but it's always base 2. And what that means is, it's always dividing by 2. Logs in computer science are easy peasy. You're going to love them. We love them. But it's because everything's base 2. Because we always like to divide by 2. Right? So it's the inverse of 2 to the n. Log base 2 of n is the inverse of that, if you wanted to. Log base 2 of 2 to the n is n. Anyways, you'll see. Okay, n log n. Often you won't even hear computer scientists say what the base is in the log unless it's not base 2. So I have n log n plus n. Well, if I have n times log of n versus n, well, n log of n times log of n is going to be a little worse than n. Right? It's not as bad as n squared. It's not n times n. It's n times the log of n. So n log n is a little worse than linear, but we'll take it. So this one here, this grows like n log n. Now 3n squared plus 5n minus 2. What's the dominant term? Well, it's the n cubed part. This is a big O, and, oh, pardon me, n squared, pardon me. The n squared is the big one. And then 2 to the n plus 3n. Well, 2 to the n is a hell of a lot worse. That's exponential. Something that grows exponentially grows a heck of a lot worse than something that grows linearly. So we would say, well, that's big O n, or 2 to the n. If you have an algorithm that's 2 to the n, you're in trouble. You don't want algorithms that look like that. They don't run on your computer very well.
Would you ever have to use one?
Oh yeah, we're going to see a couple. And so if you plot these things, maybe there should be another plot here that also has log n that's better than n. But if you plot all these things, you kind of get a sense of, well, okay, n cubed would be really steep, n squared, not as bad as n cubed. N log n is between n squared and n. Log n would be better than n, but worse than constant time, right? These right here are like your most common ones that you're going to find. They really are. You can go to the Wikipedia article. Here, look at that. Here's the Wikipedia article on the common functions that you see. And you look at them all and you go, oh wow, there's actually not a lot at all. We have order 1, that's constant. Log n, okay, that you don't really see very often, but I guess, could pop up. Log n to the power of some constant, you don't really see that one very often. N to the c, well that is, okay, that would be like a root, right? Because it's some value, some constant less than, some value less than 1. And these are not very common. And log n, but I don't even know what that is. Let's just ignore that one. I don't even know what it is. N log n, n squared, n to some constant greater than 2, I guess. C to the n, that would be like 2 to the n. And then the big bad boy is n factorial. You don't want that one. But that traveling salesperson problem I talked about last time, the naive solution, the naive strategy that I said, just try every possible combination and just pick the one that's the best, that's a factorial. You don't like those. They're not good. So anyways, there are some common ones. Oop. So here I'm going to test you now. Let's test you. if I give you the growth function 5n squared plus 3n, what is it? Why?
Because n squared is the one to blame.
Yes. Who's to blame? N squared. Why? Because it's the one to blame. Honestly, though, that's sufficient. Okay, how about n cubed log n? N cubed, absolutely. Because n cubed grows faster than the other bits. 10n log n plus 5.
10 log n.
N log n. How about 3n squared plus 3n cubed plus 3? 3n cubed. And how about 2 to the n plus n to the 10? 18n to the 10. 2 to the n. Yeah. Even though n to the 10 is real bad, eventually exponential is going to be worse. Right? So, yeah. There you go. You're experts at this already. Now, of course, we haven't talked about where we get these growth functions from. We talked about how to go from a growth function to the big O. How do we derive a growth function? Well, first I'm going to show you how we can do that pretty easily. But second, I'm going to show you how we just kind of like to skip that anyways and go straight from the code to the big O. All right? So growth function is derived by looking at the code. For simplicity, constant time, constant time stuff is going to be said to take 1 unit of work, even though that might not be true, but the point is it's constant time work, so that's all that really matters. Yeah?
I was just going to ask before we go farther, what on the graphs, what's on the y-axis? Like, what is that measuring?
That is like units of work.
Like how, yeah.
It's not anything precise, it's just as it gets, the amount of work required would grow at this like rate. That's the important thing. So you're right. That's a good question. No, there's not. It's not like you can be like, well, that's how many floating point operations your computer's doing. No, we're not touching that right now. That's far too specific. All right. So here's a couple of statements. Each of these statements is constant time work. There's really no magic going on here. X equals 0, y equals 1, z equals x plus y. They're all 1 unit of work. Even though really, maybe the addition's a couple more steps involved for your processor, the point is it's constant time, so I'm going to count it 1. So here I'd say like, well, the growth function is like t of n equals 3. So if I ask you, what's t of 10, what's the answer? It's not a trick question. 3. T of a billion. 3. Exactly. It doesn't change at all depending on what n is. N has no impact on this. So when you have code that looks like this is just constant time code. There's nothing magical going on here. Loops. This is where things get interesting. So, the number of times a loop executes might depend on some value n. For example, look at this for loop. I is 0, well, it's less than n. Okay? Now, that outside thing, that x equals 0, is 1 unit of work. The x equals x plus 1 is 1 unit of work. However, how many times is that 1 unit of work going to run? How do you know? It's too stupid of and it has too obvious an answer that it seems like a stupid question, right? Why? Because the loop runs n times. So if I have to do 1 unit of work n times, how much work did I do? 1 times n, yes. Who said it? Absolutely correct. 1 times n. N. So, outside the loop, we had 1 unit of work. And then the inside, the loop part is then 1n. So that's the growth function. But here I would say, well, that's big O of n. It's linear. Because the only thing that really matters is the loop part here. If I double the size of n, that constant time work that's taking place inside the loop gets run twice as many times. So here is this loop, it's linear. The trick really when investigating iterative code is look at the loops. Look at the loops. Think of it like this too. I always like to think of it as like a number line or something. How many things do I have to put my finger on? I start at 0, put my finger on 0, and then the 1, and then the 2, and then the 3, and so on, 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 and so on. Eventually I hit the n minus 1, well 0 through n minus 1, that's n things. Nested loop. Okay, any questions so far? It's nothing magical. It's quite intuitive, actually, right? If it was any more complicated than that, computer scientists wouldn't do it. Nested loops. This is, now it can get a little trickier. Outside the loop, x equals 0, y equals 0, that's constant time work. But I think it's going to be easier to work ourselves from the inside out. So let's go into that inside loop. Line 6. Y equals y minus 1. How much work is that? Yell.
N times n.
Well, hold on. Oh, no. I asked a very specific question. You're jumping ahead. You're right, but you're jumping ahead. Line 6. How much work does line 6 do in and of itself? People are going like this. It's 1. But how many times does that inside loop run? N. So, pardon me. So let me rephrase that question to make sure I'm clear. How many times does line 6 get run as a consequence of the loop on line 5? N. But how many times does the loop on line 5 run? Another n times, right? Yeah, so we have line 6 is 1 unit of work. But we're running that line n times as a consequence of that loop on line 5. And then next to that I have another constant time amount of work. Right? So I have n plus 1. But I'm running that n plus 1, or perhaps maybe I should say 1 plus n, amount of work n times. That's this. That's this right here, that 1, okay? That is the x equals x plus 1. 1n here, that is the loop from line 5 to line 7. But I'm running that loop because of the loop defined on line 6 n times. And then I'm doing 2 units of work outside the loop because I am. So in total, this is my growth function. It looks like that I can simplify to n squared plus n plus 2. When I look at that, though, I look for the dominant term. What is it? N squared. When you see nested loops, your brain maybe should be going n squared. Assuming there's 2 nested loops. Any questions about that? It got quiet, so I don't know if it's because you're tired or because it got confusing.
I'm ready for it now.
You're ready for a nap?
Yeah.
Yes.
My question is, since it's 2n, because you have one nested loop and another loop, if you had like another loop nested in that, would it be n to the 3?
Yeah. I mean, we could calculate it out if you had the code, but typically you see 3, you go like it's n cubed, because you have to run it n times n times n times.
Would it ever not be that? Or?
When it's nested, it might not be, depending on a lot of the different funny things. But your brain should go typically to think nested, that's going to be like to the power of. Alright, so consider the below n by n matrix. And the reason it's n by n is the loops are both running n times each. And n doesn't change. The y equals y minus 1 is represented by a single spot. That one single operation, y equals y minus 1, is a single point in this matrix. One of these little cells. Okay? the loop that runs n times, the loop from line 5 with the j, represents a row of it. One row. Because I'm running each of those spots n times. So I get a row. But then I'm running each of those rows n times. So that's how I end up with all of the rows. So in my mind, when I see nested, I don't think of a number line, I think of like a matrix. And if I have to put my finger on each of these cells in the matrix, I have to do, well, n times n of them. Any other questions about that? All right, now here's a test. I'll give you a second, look at this code. Maybe talk amongst yourselves. Don't give it away such that everyone else hears it, but talk amongst yourselves and tell me, what is the growth function and or the order, the big O, of this code right here? The hint, is nice. The hint is nice. And raise your hand when you're confident that you have a solution. 2 people. Still seeing some people actually talk about it, so I'll give you a second. Okay. All right, so raise your hand if, and I promise I won't just arbitrarily call on one of you, so I won't put you on the spot. Raise your hand if you're like, yeah, I've got an idea in mind. Maybe you're not that confident about it, but you have an idea you've locked in your mind. I saw you go, you half have an idea in your mind? A little bit. Okay, who wants to tell me what they think the growth function is?
1 times n divided by 2 plus
1 times n divided by 2 plus 1. So half n plus 1. Raise your hand if that's what you said the growth function is. Okay, so it looks like other people had different answers. What else do we got? All right, I'm not seeing any other answers, but yes, absolutely right. The growth function is half n plus 1. Or, because it's half n, what is the time complexity then? What is the big O? N over 2? No.
1.
No. N. Because we don't care about the coefficients. Coefficients we don't care about. And half n? Half? That's just the coefficient. So we don't care about it. So it's kind of a trick question, right? And if you're wondering, why is it half n? Well, what am I incrementing I by? 2. So if I have to go from 0 to n, and I'm putting my finger on all n things, 0, 1, 2, how many things am I putting my finger on? But if I go from 0, I skip 1 and go to 2. I skip 3 and go to 4. How many things am I going to put my finger on? Half of them, because I skipped half of them. Yeah. Good. It's just n, order n, it's linear. Good. Half n.
Oh, right, yeah. So it'll just be, okay. I got it. Sorry.
How about this one? This one's a tricky one.
I don't like this one.
You don't like it?
No.
Don't worry, it's easier than you think. Remember, computer scientists are lazy, we're not smart, we can't do anything complicated.
Is it n squared?
Is it n squared? Yes!
Oh my goodness. So smart.
Now, here's the thing. The reason this one's tricky is, look, each time through the loop, j starts at I. Right? If j started at 0 every time, this is what would happen. I would have j start at 0 and go to n. And then the loop would rerun again, right? From 0 to n. The loop would run again from 0 to n. And that would happen a total of n times, right? But that's not what's happening here. What's happening is I'm starting j at I. And I is incrementing every time. So really what's happening is, the first time through the loop, I'm going 0 to n. The next time through the loop, I'm not starting at 0, I'm starting at like 1. I'm starting at 2. So the amount of work I have to do on each row gets smaller and smaller and smaller and smaller and smaller. All the way down to like at the end, right? Each time through the loop, I don't have to put my finger on as many things. But it's still n squared. And there's a couple of reasons why we could conclude this. One is be lazy computer scientists and be like, well, it still looks like a square, right? Just we cut half of it away, right? And cutting half away is something, half is just a coefficient, we don't care about those. It's n squared, right? That's how I'd conclude it. Now if you want to be fancy, and this is a callback to last semester, because I'm pretty sure I did this analysis last semester with you. If I can find a marker that actually works. Oh, decent. First time through the loop, how much work is getting done? N. Okay. Next time that outside loop is doing its thing, how much work does the inside loop have to do? N minus 1. But it's additive though, right? So it's n plus n minus 1, right? Next time through the loop, how much work is there going to get done? Come on. And eventually it's going to get down to the point where we get down to like 3, 2, 1, right? Eventually. Does this look familiar to anybody? Say yes.
Yes.
Now, what does it remind you of? Factorial. It is reminiscent of that, but that's not what this is. Oh, come on. You all just said it reminds you of something. What does it remind you of? A sorting algorithm. No. It looks like some sort of series. A Taylor series. Oh, interesting. Can anyone name this kind of series? What operation is happening? Some call that an arithmetic series. Whoa. Some people call it that. Of course you all remember this now, right? And you all remember that simple little expression we use to calculate the sum of any arithmetic series, right? You all remember that, right? Right?
Yeah.
So who can tell me what it is? Holy moly, I didn't think anyone would do it. N times n plus 1 over 2. Absolutely it is. Who remembers how to derive that?
Take the top top series, reverse it,
Perfect.
add them together, and divide by 2.
Perfect. Here's how. You're never going to forget how to rederive the arithmetic series again, even though I said this last semester, and it seems like everyone forgot but you. Did you even take 161 with me last semester?
I was at a different
Jesus Christ. God damn it. Well, now you'll never forget. Here's the trick. The trick is you Google it. Yes. No, what you do is we go, you know what? We're going to double this series, but we have to put a pin in it. We're just going to arbitrarily double the number of numbers in this series. And I'm going to write those numbers again in reverse right below it. Where I put it really doesn't matter, but it's going to matter for showing you. So I'm going to put 1 right here, plus 2, plus 3, plus n minus 2, plus n minus 1, plus n. Right? And for the sake of space, plus 2, plus 1. Right? Then what I do is I go like, wait a minute. What is n plus 1? Because this is arithmetic. I can add n plus this, plus this, plus this, plus this, in any order I want. It's all going to add up to the same thing in the end. So I'm going to start by going, look at this. What's n plus 1? Yeah. And what's n minus 1 plus 2? What is n minus 2 plus 3? I'm seeing a pattern.
Oh, it's you multiply by.
What's 3 plus n minus 2?
N plus 1.
What's 2 plus n plus minus, I'm just going to write it.
Plus 1.
How many n plus 1s am I left with? N of them. How do you know? Well, because that's how many numbers there are. So really, I could just say, well, that's n times n plus 1. But what did I do to my numbers? I doubled them. So we got to undo that double. How do we undo a doubling? Divide by 2. Oh my God. And if we multiply this out, we get like a 1/2 n squared plus n. Get rid of all this, right? N squared plus n. Oh my God, it's n squared. Look at that. Or be the lazy computer scientist and say, it looks like a square. All right, I'll see you later.